You are watching video series for grade 10 advanced. In this video we are discussing chapter 1 lesson 2 wave properties, and we will be talking about what is a wave, longitudinal and transverse waves, wave properties, that is wavelength, time period, frequency and amplitude, energy of a wave, speed of the wave, phase, in phase and anti-phase. Dear students, this is Amir Shahjahan. Welcome to this beautiful channel, Mass Academy. In general, there are two different ways for transfer of energy. One is through the movement of the particle, through the transfer of the particle. For example, I am giving my energy to this marker and I am throwing the marker. Means I transfer my energy to the marker. And this marker carries that energy and it travel, right? It travel. For example, I want to break that bulb. So I transfer my energy to the marker and I throw the marker. When I throw the marker, I am transferring my energy to the marker. So the marker travels carrying that energy and it will go and hit the bulb and it will break the bulb. So here energy is transferred through the movement of the marker to the transport of the marker. That is one method. Second method is through waves. So what is a wave? A wave is a disturbance. A wave is a disturbance that travels through a medium. Why do they travel through medium? The disturbance travel through a medium transporting energy. Transporting energy from one place to another without transporting matter. So what is a wave? A wave is a disturbance. A wave is a disturbance that travels through a medium for transporting energy without transporting the matter. So what is a wave? A wave is a disturbance that travels through a medium transporting energy from one place to another without transporting matter. For example, here you are in your school assembly line. So the students are lined for the school assembly. So this each dot represents each student. So you are standing here. You are standing here, and what you are doing is you are just moving and falling onto the next student. You are moving and falling onto the next student. Like this, you are standing in the line, the next student standing here, the next standing there, the next standing there. What are you doing? You are falling and you are moving and falling onto the next student. For what? You're doing it for fun. You're doing it for fun. Fun for you. But it's a disturbance for the teacher. So we will take that's a disturbance. So here you are going and falling onto the next student. And after that you are coming back to your place. Then what the next student is doing? He is falling onto the next and he is coming back. Then he is falling onto the next, coming back to its original position. Falling onto the next, coming back to his place, falling, going and falling onto the next, coming back. So here you can see what happened. The disturbance is traveling, right? The disturbance is traveling from one place to another. The disturbance traveled from here, from you. You are here. So the disturbance traveled from this place to here, to this end of the line. But you didn't travel. You are here, right? You just moved, then came back. You just moved to the next student, then came back. So here you can see what is a wave. A wave is a disturbance that travel through a medium without transporting the matter. So here you can see the disturbance traveled, right? The disturbance traveled from here to here, from this end of the line to this end of the line, but the students didn't go. The student didn't go to here. Only the disturbance traveled, but the student just moved, or we can say the student is moving forward then backward. So here you can see the particles of the medium, that is the students in this example or in this analogy, they are moving along the direction of travel of the wave, right? So here in which direction the disturbance is traveling? The disturbance is traveling along this direction, and the student also moving along this direction, right, or parallel to the direction of travel of the wave. The student is moving parallel to the direction of travel of the wave. So if particles of the medium, if particles of the medium, if the particles of the medium vibrate parallel to what? Vibrate parallel to the direction of travel of the wave, direction of travel of the wave. So this type of wave is called longitudinal wave. That is one type of the wave. Okay, longitudinal wave. Longitudinal wave. What is a wave? A wave is a disturbance that travels through a medium for transporting energy from one place to another without transporting the matter. These waves are classified into two types: longitudinal waves and transverse waves. Longitudinal waves and transverse waves. What is longitudinal wave? In a longitudinal wave, particle vibrate parallel to the direction of travel of the wave. So longitudinal wave, you remember this keyword parallel. Whenever you see longitudinal wave, whenever your teacher tell longitudinal wave, or when you see the longitudinal wave in the question paper, remember this keyword. You need to connect longitudinal wave with parallel. In longitudinal wave, particles of the medium vibrate parallel to the direction of travel of the wave. So what is transverse wave? What is a transverse wave? For example, this is your assembly line. You are here in your assembly line. So students are standing in the line very obediently, and what you are doing? You are jumping. You are jumping for what? For fun. You are jumping for fun, so that is a disturbance. That is a disturbance. In the school assembly, that is a disturbance. Then the next student, he see you are jumping. He is also jumping. When he saw that this student is jumping, he jumped, just jumped like this. Then this student see that he is jumping, he is jumping, he is jumping. So here the disturbance traveled, right? The disturbance traveled from you are here, to this end. So disturbance traveled along this direction, right? Disturbance traveled along this direction, but in which direction the particle is moving? Particle is moving up and down, right? Up and down. You can see particles are moving up and down. Down spelling D-O-W-N. So particles are moving up and down. So here you can see what is this angle. This angle is 90 degree, right? So particles are moving perpendicular. 90 degree means perpendicular. So particles are moving perpendicular to the direction of travel of the wave, this type of waves are called transverse waves. In transverse waves, particles vibrate perpendicular to direction of travel of waves. Whenever you see transverse waves, remember this keyword, perpendicular. In transverse wave, particle vibrate perpendicular to the direction of travel of the wave. So we have studied what is a wave. A wave is a disturbance that travels through a medium to transport energy from one place to another without transporting matter. Waves are classified into two types: longitudinal waves and transverse waves. In longitudinal waves, particles vibrate parallel to the direction of travel of the wave, and in transverse waves, particles vibrate perpendicular to the direction of travel of the wave. Then what is an example for a longitudinal wave? We will take sound wave. Sound waves is a longitudinal wave. And what is an example for a transverse wave? For example, if you produce wave in a string like this, I take a rope, I take one end of the rope and making like this. So the wave produced in a string like this or like this. The wave produced in a string is an example for the transverse waves. Wave produced, wave in rope is an example for transverse wave. Now I will erase this. I hope you have written. If you have not written this in your notebook, you can pause the video and write it down. Now we will talk more about longitudinal waves and transverse waves. So I take this analogy to explain the longitudinal waves. You are in your assembly line of the school. All the students are lined up in a straight line. So what are you doing? You are moving and falling onto the next student, right? So when you are moving and falling onto the next student like this, you are moving and falling onto the next student, so you will be here. Then you can see this area become empty space, right, without student. This we will call low pressure region. Low pressure region. Low pressure region is called compression. So this one you can see here. Now this is like crowded, right? So you are falling on to the next student. So that area become crowded. Here two students together. So this we will call, this area we will call high pressure region. High pressure region. High pressure region, sorry, low pressure region is not called compression, okay? By mistake I wrote compression. Low pressure region is called rarefaction. Rarefaction. And high pressure region is called compression. Okay, then this student, you will come back, right? You will go back, and he will go and fall to the next. So this high pressure region is moved here, means the compression moved here, this area become compression, and this area when he is going back, that become rarefaction. Okay, so next you can see this one, this student, he will move here, so this become compression and this point become rarefaction. When he moves and fall, this become compression and this area become rarefaction. When he move and fall onto the next, this become compression. So you can see the compression is moving, right? The compression is moving from one place to another. So here this is compression and this area will be rarefaction. Then what is an example for a longitudinal wave? We said sound is a longitudinal wave, right? Sound wave is a longitudinal wave. So when I talk, what happens is, when I talk a sound, means when I produce a sound, so the sound energy coming out of my mouth, the pressure coming out of my mouth will push the air particle. Those air particle will move and hit the other air particle, like the student falling and hitting to the next student. The air particles will move and hit. So when they hit, that area become high pressure region, and this area where the air is moved, this become area without air, right, or area with less air, that become low pressure region. And the air moved and hitting the next air particles, that area become high pressure region, compression. Then those the air particles moved, it will come back to its original place. Then the other air particles will move and hit the next. So compression will be moving from here to here to here, like that. When the air particles and move and hit the other air particle, the compression is actually moving. So if I draw that air particles like this, if I draw here like this, not in the air particle, like random arrangement, right, not in an order. So like this, and I am talking from here, I am producing a sound from here, and this is the ear, someone hearing this sound ear. Okay, yeah, good drawing. Then what happens is, when I produce the sound, the air particles will move, right? For example, this air particle, will move and hit to the next. This will move and hit to the next. This will move and hit to the next. This will move and hit to the next. So this area where the air particle is moving, it become low pressure region. Low pressure region is called rarefaction, right? Rarefaction I will represent by the letter R. It represents the rarefaction. Rarefaction is the low pressure region, and all these air moved, or some of those air moved here. So this area become high pressure region. High pressure region is called compression. Now what happens? This air will come back to their original position, and this air will be moving forward, right, to hit the next air particle. So what happens? This compression will move to the next. The compression will move to the next. Then this happens if there is a wave pulse. Wave pulse means there is only one disturbance. One disturbance is called wave pulse. Like I make a sound beep, e, that is a pulse of sound. So if I make a continuous sound, if I talk like this continuously, or if I make e sound, so what happens is there will be continuous, like alternate compression and rarefaction. Alternate compression and rarefaction. If there is a pulse, only one disturbance, the compression will be moving, right? So if I take like beep, 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 like this continuous sound, when this compression move, next compression will come, next sound, next pulse, like that continuously I am emitting pulse. So what happens is, in a wave there will be alternate rarefaction and compression. This is rarefaction, this is compression, rarefaction, compression, like this. So if a wave is traveling, if a sound wave is traveling through air or through any medium, there will be alternate rarefaction and compression, rarefaction, compression, rarefaction, compression, a pattern of alternate compressions and rarefactions. What is compression? Compression is a point of high pressure region, or compression is the high pressure region and rarefaction is the low pressure region. And when a sound wave is traveling, there will be alternate compression and rarefaction. So in this analogy, what is the meaning of compression? Compression means you are falling and hitting to the next student, right? So there will be like two students together, right, at that time. So it is crowded, right? That crowded point, that is analogy. Okay, crowded point is called the high pressure region, that is compression. So here you can see, students, this is one compression to the next compression. So the distance from, I will take the distance from the middle, okay, from the middle of one compression to the next compression. So this distance, that distance is called wavelength. So distance from one compression to next compression, or distance from one rarefaction to the next rarefaction. That if you start from here, if I start from here, then from here to here, starting of the rarefaction to the starting of the next rarefaction. If we take from the middle of one rarefaction, then to the middle of the second rarefaction, or distance from one compression to the next compression, or one rarefaction to next rarefaction. Means from one low pressure region to the next low pressure region is called wavelength of the wave, is called wavelength. Wavelength we represent by this Greek letter lambda. So what is wavelength? Wavelength is the distance from one compression to the next compression. This is wavelength. This length from one compression to the next compression, or one rarefaction to the next rarefaction, that we will call, that distance we will call wavelength, and wavelength we represent by the letter lambda. When I go to the transverse wave, so here students, you are jumping in this line, you are in this assembly line. So what you are doing, you are jumping, like when you see, okay. So here you can see the wave is traveling along this direction. So transverse wave means perpendicular, right? Perpendicular. So here you can see, like when this wave is traveling, some student jumping, moving up. Jumping means moving up then falling down, right? Moving up and falling down. So moving up and down, right? Up and down. Example for a transverse wave is wave produced on a rope. So here we have a rope here. I am taking one end of the rope and shaking like this, moving up and down, So this disturbance will be traveling through the rope to the other end of the rope. then the particles in the rope will be moving up and down. It will be moving up and down. That if you take a rope and do this, you can visualize that, you can see that. So the rope become like this, right? When I shake up and down like this, so the wave will be produced like this in the rope. Rope will be moving like that, right? Rope will be moving up and down. Then the disturbance is traveling from one end of the rope to the other end. So here you can see there will be some part of the rope moving up, right? This is called crest. The part of the rope moving up is called crest, and part of the rope moving down is called trough. Crest, then trough, like that. So in a transverse wave there will be alternate crest and trough. Crest means part of that medium moving up, trough means part of the medium moving down. That you can see in water waves. Water wave is an example for transverse waves. Water waves, you can see water particles moving up, water particles moving down. Water particles moving up, the particles of the water, or the part of the water moving up is called crest, and part of the water moving down is called trough. So there will be alternate crest and trough in a transverse wave. So what is the meaning of wavelength? Wavelength is the distance from one crest to the next crest, one crest to the next crest, or one trough to the next trough. The distance from one crest to the next crest, or one trough to the next trough, is called the wavelength lambda. Wavelength we represent by the Greek letter lambda. The next we will talk about the properties of waves. So I will erase this part. We will talk about the properties of waves. So how to represent a wave? A wave we represent like this, as we have drawn here. This one I will draw first. We will represent a wave like this. So a wave here, crest, trough, like this, we will represent a wave. So here this represent the crest, right? Crest, this represent the trough, crest, trough. So in a transverse wave, crest means the part of the medium moving up, trough means the part of the medium moving down. And here if I draw this wave, the sound wave, if I represent as a wave diagram, so compression, rarefaction, compression, rarefaction, compression, like this. So this part represent this upside, means in the diagram, okay, in the graphical representation of wave, here particles are not moving along the particles are not moving perpendicular like this. So this is just a graphical representation. In this graphical representation of longitudinal waves, this upside represent crest, upside represent compression, see, correct, compression, and the downside represent rarefaction, compression, rarefaction, compression. So this is crest, trough, like that. Now we are talking about the properties of waves. Number one, wavelength. Wavelength already we have discussed, represented by the letter lambda, and you know that what is wavelength, so I am not repeating that. Number two is the second property that we will talk about, the amplitude. Amplitude we represent by capital letter A. What is amplitude? Amplitude is the the maximum distance from the equilibrium position. So what is equilibrium position? Equilibrium position is represented by this line in the middle. This line in the middle represents the equilibrium position. So what is amplitude? Amplitude is the distance from here to here, or distance from here to here. This distance. The maximum distance, amplitude is the maximum distance from the equilibrium position, that is called amplitude. So we will write here what is amplitude. Amplitude is the maximum displacement from equilibrium position. Maximum displacement from the equilibrium position. What is the unit for amplitude? We measure amplitude in meter. We measure wavelength also in meter. Then number 3, the third one is the time period. Time period we represent by the letter T, and the SI unit for time period is second. What is the meaning of time period? Time period is time taken to complete one wave. What is the meaning of one wave? One wave is one compression and one rarefaction in a longitudinal wave. In a transverse wave, one crest and one trough. So it is the time taken to complete one wave, that is called a time period. Or we can say, I said, like for example here, when I talk, the air particles are vibrating, right? In a longitudinal wave, air particles are vibrating along the direction of travel of the wave. So the time taken to complete one vibration. What is the meaning of one vibration? For example, this is the air particle here. So when I talk, this is moving forward, then it will move back, then will go to the original position. That is called one vibration. Like you sing, right? Sing, for example, it is starting from the middle, coming here, going forward, coming back to the midpoint. That is called one vibration. So the time taken to complete one vibration, or time taken to complete one cycle of the variation, means one cycle. What is the meaning of one cycle? One cycle is one crest and one trough. That is called one cycle. One cycle consists of one crest and one trough, or one compression and one rarefaction. So time period is time taken to complete one wave or one cycle of the wave. So time period is time taken to complete one wave, and during that time the wave will travel a distance, right? That distance is actually called wavelength, or that distance will be equal to wavelength. The next we will talk about the fourth one, frequency. Frequency, how many waves, number frequency we will represent by F, and the SI unit for frequency is hertz. Hertz, okay. Hertz is the SI unit for frequency. So what is frequency? Frequency is how many waves completed in 1 second. How many waves completed in 1 second, that is called frequency. For example, if I produce like sound like beep, 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 or e, 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 like that, each time when I produce that, each pulse, each sound, the particle will vibrate like this, right? One vibration, e, second vibration, e, third vibration, e, fourth vibration. So if I make like 10 times that sound, if I produce that sound 10 times, the particle is vibrating 10 times in 1 second. If I produce that sound 10 times in 1 second, then particles vibrate 10 times, right, in 1 second, or there will be 10 waves in 1 second. So number of waves produced in 1 second, that is called frequency. Number of waves number of waves produced in 1 second. Okay, number of waves produced per second is called frequency, and the SI unit of frequency is hertz. We will represent frequency by small letter f, and there is an equation, a relationship between frequency and wavelength. So what is the relationship between frequency and time period? We will write that relationship here. Frequency and time period, we can write frequency is equal to 1 over time period. 1 over time period. So I will write period. Frequency is equal to 1 divided by time period, or I will write this like this. Frequency we represent by the letter f. So frequency is equal to 1 over time period, that we represent by capital letter T. So this is the relationship connecting frequency and wavelength. Then of course you know this, right? So time period will be equal to 1 by frequency. Let us talk about the energy of waves. Energy of waves. We know that the waves produced, the big waves produced in the sea by a strong wind, by a storm. The big waves produced, very big waves produced in the sea by strong wind will have greater amplitude, right? It will have greater amplitude, the greater size. That waves will have much energy or greater energy, very large amount of energy. And the waves in the sea produced by a gentle breeze will have lower amplitude and lower energy. Do you understand? The waves produced by strong wind means strong wind transfer a lot of energy to the water. So the waves produced will have greater amplitude, the greater size, and it will have more energy. And the small waves produced in the water by gentle breeze will have less energy. So we can say the waves, the energy of a wave that is directly proportional to the square of the amplitude. Energy of a wave is directly proportional to the square of the amplitude. For example, we have a wave here like this. So its amplitude is like 1 meter. 1 meter is the amplitude. And another wave like this. So its amplitude is like, for example, 2 meters. And if its energy is, for example, if its energy is 10 joule, then what will be the energy of this wave? Energy of a wave is directly proportional to the square of the amplitude. Energy of a wave is directly proportional to the square of the amplitude, means when amplitude increases, the energy of the wave will increase. When amplitude increases 2 times, the energy will increase by 2 square times. By 2 square times. What is 2 square? 2 square is 4, right? So energy will increase 4 times. When amplitude increases 3 times, when amplitude increases by 3 times, then energy will also increase. Energy will increase by 3 square times. What is 3 square? 3 square is 9, right? So energy will increase by 9 times. So here the amplitude is increased. In this amplitude increased by 2 times, right? So if amplitude increased by 2 times, then energy will increase by 4 times. So energy will be 4 times the previous energy, 10 joule. So here energy will be 40 joules. Then we will draw another wave here. Another wave. So it has an amplitude that is 3 meters, 3 meter means amplitude increased by 3 times, right? 3 meter. So if amplitude increase by 3 times, what happens to energy? Energy will also increase how? By 3 square times. So how much is 3 square? 3 square is 9 times. So 9 times its energy 10 joules, so it will be 90 joule. So that is the relationship between energy of a wave and its amplitude. If the wave is larger wave will have greater amplitude, then it will have greater energy, and the wave, smaller amplitude, smaller energy. And you can see here, energy of a wave is directly proportional to the square of the amplitude, which means when amplitude increases by 2 times, energy will increase by 2 square times. When amplitude increase by 3 times, energy will increase by 3 square times. 3 square is 9, so energy will increase by 9 times. When amplitude increase by 4 times, the energy will increase by 4 square times. 4 square is 16, so energy will increase by 16 times. The next we are talking about speed of a wave. Speed of the wave. Speed of the wave or speed of a wave. Speed of a wave. What is the meaning of speed? You know that, right? Speed, very basic concept. Speed is distance traveled in 1 second, right? So speed of a wave is distance traveled by a wave in 1 second is called speed of that wave, is called speed of that wave. So if a wave travel like 2 meters in 1 second, its speed is 2 meters per second. If a wave travel 3 meters in 1 second, its speed is 3 meters per second. So what is the equation to calculate speed? The basic equation, right? That everybody knows, speed is always equal to distance divided by time. The distance traveled divided by time. And what is the unit of speed? Unit of distance is meter, unit of time is second, so unit of speed is meter per second. What is speed? Distance traveled by a wave in 1 second is called the speed of the wave. Speed is equal to distance divided by time. So here for wave we have one more equation to calculate the speed of the wave. Speed of a wave, the second equation, okay, this is one equation to calculate speed. This equation you can use to calculate speed if distance and time is given, and second equation, speed is equal to, so this is a special equation for the speed of the wave. Speed is equal to frequency of the wave multiplied wavelength. Frequency of the wave multiplied wavelength. Speed we will represent by the letter V, frequency F multiplied wavelength lambda, and this equation is called wave equation. Wave equation. This equation is called the wave equation, and in the next video we will discuss all the questions that is given in the textbook. And the last concept, we will talk about the phase in this video. We will talk about phase of a wave. Phase. Then in speed of the wave, I want to add one more point, that is speed of a wave. Speed of a wave depends only on the medium. Speed of a wave depends only on the medium. For example, speed of a wave will be different in different medium. Speed of sound wave in the air at 20 degrees Celsius is 343, and the speed of sound will be greater in water, in liquids. the speed of sound will be greater compared to the speed of sound in the gas. In solids, the speed of sound will be even greater than the liquid. So speed of sound depends only on the medium, which means speed of sound does not depend on the amplitude or speed of a wave. Okay, speed of a wave does not depend on the amplitude of the wave. When you increase and decrease the amplitude, there will be no change in speed of the wave, and speed of the wave will not depend on the frequency, and speed of a wave does not depend on the wavelength. Speed does not depend on all these things. No. Speed depends only on the medium. When medium changes, speed of the wave will change. Now we will talk about phase. Phase. I have given this example as not example, an analogy to the transverse waves. For example, you are jumping like this. So that is only one time you are jumping, so it is a pulse. When the disturbance happens one time, a single disturbance is called a pulse. For example, if you are jumping each time, means you are jumping like in each second. So what happens after that? He is jumping, after that he is jumping, after that he is jumping, after that he is jumping. Then like for example, when he is coming down, you will be jumping your next, right? Like that. So for example, when you do your third jump, then when you reach here the maximum height, so he is also in the maximum height. Then next he reached the maximum height here. So like these three particles are in the same state of vibration, right? They are jumped and they reached the maximum height. So what will be happening? They will be in other state, like maybe coming down after their jump. Like you are completing your third jump, so this will be completing its second jump and falling down. So phase means state of vibration of the particle, state of vibration of the particle. So here you can see like these three students are in the same state of their movement, same state of their vibration. If particles are in the same state of the vibration, we say those particles are in phase. And if the particles are in the opposite state of vibration, one is at the maximum highest point and other is at the lowest point, so this is called antiphase. For example, if I draw this wave, like this. So here in this wave you can see this particle at its maximum displacement, the particle here at its maximum displacement, wave in a rope. Okay, this represent wave in a rope. So this rope at here is at maximum displacement, the rope at here is at maximum displacement. So all these points are in the same state of vibration, right? Same state of motion. So that is called, these points are in phase. These points are in phase. For example, if I write A, B, C, D, all these points are in phase. Then if we take another point like this one, this one, this one, so this I will give like 1, 2, 3. These points also in phase, right? 1, 2, 3, or like what is their state of vibration? The maximum displacement downward, maximum displacement downward, maximum displacement downward. So they are in same state of vibration. So we can say 1, 2 and 3 are in phase. But if we talk about, like for example, A and 1, point A and point 1. So point A is at its maximum displacement in the upward direction, and the point 1 is at its maximum displacement in the downward direction. So A and 1, they are in antiphase, they are in the opposite state of vibration, so they are antiphase. What about A and B? A and B, they have A as maximum positive displacement, at the same time B also has maximum positive displacement, so A and B are in phase. What is the meaning of antiphase and in phase? Antiphase means opposite state of vibration. In phase means same, they are in same state of vibration. So particles are in the same state of their vibration at that time is called they are in same phase, and particles they are in opposite state of vibration, then we say those particles are in antiphase. I hope you understand these things, and this is the end of this video. Thank you students for watching the video. Good luck.